great to see you, Casey.
You too.
It's been a while.
Yes.
And Casey presented at Raw Crystal 2020 7 months ago. So great to have you for an extended time this time around. We got 30 minutes to spend together.
Okay, great. So yes, as Lorenzo said, my name is Casey Erb. I'm a physicist and a software developer both. And today I want to tell you why I choose Crystal for science. I also want to challenge you today to help pave the way to help other scientists make that same choice. And that's because I expect and hope to still be reading Crystal code 40 years from now. And that might sound hard to believe, but I think I can explain a few things that'll make that dream seem like more of a reality. The first one is that things don't change that much at the foundation of math and science and code. There are some programs and algorithms in the scientific world that are so foundational that they haven't changed in more than 40 years. If you take a look at this file here, we can see that the author is listed there on the third line, and his name is Jack Dongarra, and he wrote this in 1978, and it was only modified again 15 years later, and mildly at that. These are just one of hundreds of subroutines that form the foundation of scientific computations today. If a computer is a number crunching machine, programs like these are the number crunchers. And so we need to attract the scientific community. In my view, languages like Node and Python are on the rise because they're providing high-level access to low-level number crunchers like these through a thriving community and a plethora of packages. Things move slower in the scientific world, much slower than in the fast-paced web world that some of us are perhaps more used to. And when the day comes that some scientific thing has a business use, think of machine learning, for example, then the longevity of those packages and their languages becomes all but assured. Now, it can be tempting to think that there's little hope for a language like Crystal this late in the game. I mean, the foundational code has already been written, right? There are only so many ways to multiply two matrices together. But don't give up before you start. While that's true to an extent, consider the following 3 points. First of all, TensorFlow. This is a machine learning library that Google wrote in Python some time ago. It has hundreds of thousands of users. You might think problem solved, right? But no. Google later wrote TensorFlow.js, the JavaScript version, and it has tens of thousands of users. Now you might think, oh, that's only 1/10, but try to remember that tens of thousands is a lot, especially considering that TensorFlow.js provides the same thing. So remember, just because something already exists doesn't mean that it can't be moved to a new language for a good reason. Second of all, you might feel like that's all good and well, but libraries at this level should be left to the experts to optimize the code. But I say that we should go just one step further and not only leave it to them, but listen to them. Back I think this one's 1993, there's another paper written to call for some of these old Fortran routines to be updated to an object-oriented style, and a description of how that was done. You might recognize the first author here, Jack Dongarra. He's the guy that we just mentioned that wrote that BLAST routine in 1978. And he had this to say: in short, we have used various important aspects of object-oriented mechanisms and C++ in the design of LePac++. These attributes were utilized not because of novelty, but out of the necessity to incorporate a design which provides scalability, portability, flexibility, and ease of use. And I'd add just one more, that's readability. See, if our code is more readable, then more people will be interested in reading it. And that means more minds thinking about the fundamental issues at hand. A great example of this is a mentor of mine who once needed to take some of these foundational routines and port them over to C++ for a research project that he was doing. In the process, he had to kind of digest that old Fortran code, and he discovered something that was surprising. He actually reported it very briefly in the paper that came out afterwards. In that paper, he said, a subroutine for the interpolation of sorted array of valuation points was written that only requires a single traversal of the input arrays. That's an algorithmic improvement on the original routines of order n plus m compared to order n times m. He later ported this to Ruby and found that thanks to the fundamentally different time complexity of the new algorithm, the Ruby code beat the Fortran code for speed. I asked him to send me this example by email in preparation for my talk, and he added this note, not knowing the topic of the talk. He said, the moral of the story is that everyone thinks that Fortran is going to be blazing fast, but order n plus m beats order n times m any day and in any language. But nobody wants to mess with the Fortran because nobody wants to have to go back and read and understand it. We can fix this. In 40 years, I hope that many will be drawn to the elegance, not only of the theories behind these numerical algorithms, but to the elegance of the code that expresses them and does so efficiently. So with that introduction to the problem, I'd now like to describe a solution in terms of what I call a hierarchy of tools. We're all tool makers, aren't we? Programmers and scientists. It's fun to craft a new tool and to show it off to your friends and loved ones. This picture is exactly how I feel every time that I write a program I'm proud of. And to be sure, that's not just tools. It's fun to make a toy, a thing of beauty, or something that you just wanted to exist. But it is tools that pay the bills. And what's more is it's new and better tools that lead the way to new discoveries. For example, in the 1600s, there was a draper named Antony van Leeuwenhoek. He wanted to see the quality of his thread a little better, and the magnifying lenses of the time didn't allow that. So he crafted his own tools, his own lenses. He is now known as the first person to ever see protozoa and bacteria. Making and honing tools is not just fun, it can change the way we see the world. In software, as in the real world, we use tools to make tools. It makes a kind of a hierarchy that way. And in our case, the tools are functions and libraries, so they're digital tools. Let's take one example. So Rosetta Code is a great resource for comparing various languages. If you haven't seen it before, then basically you can take a common task like reading and writing CSV files and see how it's done in different languages. So I'm going to take a look at a few languages that are particularly popular in science. C++ and Julia were the two that I picked for this example. And I want you to compare them and ask yourself that if right now you needed to read and write a CSV file, which languages would you choose? So first up, here's the C++ code that was submitted to Rosetta Code by a programmer somewhere in the community. And I actually can't display it on the screen in its entirety without making it illegible. So it gives you some idea of the complexity here. If we compare that to the Julia, then I think it's pretty clear which of these is more succinct. What's more is the Julia code is quite readable. It says csv.read, some csv.write. It's really clear to see what's going on here. Let's look over what the Crystal code is on Rosetta Code. There's none yet on Rosetta Code. Well, that's okay. We can go ahead and write some of our own, right? So let's look at the documentation. There's a CSV class. It says that there are several ways of parsing a CSV file. There's a slower and efficient one. Let's see, there's a CSV parser class. And if you want to write, then you need to use the builder. And this does not look like it's going to be as succinct as the Julia example. This is bad news, right? But no, it's not, because we're actually looking at this a little bit wrong. So it's going to be okay. Let's take a little bit closer look at the CSV example and consider this hierarchy of tools idea. So at the bottom, we have some root language, and built on that is a standard library. And then we build packages using that. And then we write out code using the packages and the standard library. And sort of at the bottom of the hierarchy, we're a little more focused on doing machine-oriented tasks. And the top is focused on making a nice experience for the user. So if we look at the Julia example now, then we can see that Julia is written in Julia and also in C. So some of the low-level stuff is being handled by C. And then there's actually a package we were using in that very succinct example called csv.jl. And then that little 5-line example is sitting on top of the package. Whereas for the C++ code, then the code we were looking at is written just directly in the standard library using C++. So we're actually comparing a level 3 code example to a level 2 code example. And that's not a really fair comparison, is it? It does make sense because Julia is a more human-oriented high-level language. So it's not surprising that the author reached for a package to solve the job. Whereas C++ is more of a low-level language. So it shouldn't be surprising that the author said, I'm going to write a CSV parser today, and did so pretty succinctly. So to make a more fair comparison, let's look at the code inside that csv.jl package. Here I selected just one file at random from what I was able to find on GitHub. And I think immediately we can tell the comparison's a little more fair. This code is obviously doing a little bit lower level task. It's doing a parsing pass over the file, the comment says. So there was some other pass. There's some code for setting up this multi-threaded approach to the problem. And when we compare that to the C++ code, we see something similar. I'm opening a file. So I'm doing this kind of low-level work that we expect to see at that level. And I think at this comparison, then the Crystal actually really shines. Here I've got this class, CSV, and in the top of the file, actually, most of it's a comment because that's the standard practice here is to document the code. The comments will become documentation. And there's a very simple method here. It's one line, creates a new parser. If we look inside the parser, we see the same pattern again. It's a class with a handful of methods. Each one is short. Each one is focused on some narrow scope. There's an abstract separation of concerns. We've handed off to a Lexer down at the next level. It's really nice. And now I think we can ask that question again with a little bit different perspective. Which tool would you use for the job? This is actually a really common question in programming, isn't it? Which tool is best? I think we all know the cautionary saying enshrined in the law of the instrument, also known as Maslow's law. He's famously quoted as saying, I suppose it is tempting, if the only tool you have is a hammer, to treat everything as if it were a nail. I've sometimes heard this warning applied to a decision about language choice, as if the language were the tool. I'd like to suggest a different interpretation. Let's look at that hierarchy again in the context of another important scientific library, NumPy. So what we have here is a hierarchy of tools. At the bottom, we have the tool BLAS for doing the number crunching. Then we have tools in the Python standard library for binding to BLAS. We have NumPy, which is providing tools that use those down the hierarchy and is intended at the top for the tool that you're making today that's going to use the tool NumPy. So we have a stack of tools here, right? Now, if those are the tools, then what role is language? I'd like to suggest that language is the material from which we make our tools. So we see at the bottom of the tool stack, we see languages like Fortran and C being used to make those tools. And as we go up, we see Python, a high-level language, being used more and more to make a high-level tool. And this is an important distinction. It is wrong to drive screws with a hammer, for sure. But is it also wrong to make hammers and screwdrivers from the same material? I don't think so. As material science has developed, we've engineered better and better materials. Today, we have aluminum alloys that can be used to make everything from an airplane to a keyboard. And the same is true of the material science of the computing world, languages. A modern language, like Crystal, can be used to build a much wider variety of tools, not just the tools at the top or the bottom of the hierarchy. This is groundbreaking. So in order to help you be successful in attracting scientists to Crystal, I now want to show you how scientists approach choosing a programming language. In my view, we have essentially three priorities. The first is speed of execution. A worst nightmare for scientists is the possibility that they could have spent months writing some simulation in a high-level language like Python, only to find out that it takes days to run, and they should have written it in Fortran from the start, like their friends said. The languages that scientists use are those that are perceived as fast. The second one is ease of use. Most scientists lack confidence as developers. They recognize that programming is a whole field of study in its own right, and that they have not studied it. So they will choose a language that is easy if they can. MATLAB and Python are popular for this reason, and Julia is a promising up-and-comer for the same reason. But this is value number two. So each of those languages has to fight to prove that they're as fast as C or Fortran to even be in the game. And the third is the community and packages. Here, I think scientists and programmers are pretty much the same. We really just want a healthy, thriving community where packages have already been written to do the heavy lifting for us so we can focus on the problem that we enjoy best. But one difference is that where a professional developer believes that they can fill in the gaps as needed, these gaps can seem insurmountable to a researcher. If two languages can convince me that they're both fast and easy, as many do, then the quality of packages will win the day. So let's look at how Crystal fares on these metrics. So first is speed. I think that attendees of this conference have seen the benchmarks and know that Crystal can be used to make fast tools, both on its own and because of how easy it is to bind to lower level libraries. For ease of use, let's take another example from Rosetta Code. This is where we're going to select a random element from an array. And when a scientist thinks of an easy language, they're picturing code like this that comes from MATLAB, Julia, Python. The task is simple, so the code is simple. And when they think of a hard language, they think of compiled languages like C++ or Go. even though the task is simple, there's still a lot of code needed to get it done. In this kind of comparison, I think it's pretty obvious which group Crystal belongs to. On the third point, all I can say is that we scientists need you, the developers here at this conference. We need your help to make the libraries and build the community. We've heard some great talks today in this session, and that community is growing. And here's another list of a few packages curated on the awesome Crystal repo. And this is a great start. Okay, so my last point today is that we need to understand our selling points in order to attract some of these domain experts to the Crystal community. The first selling point, in my view, is expressiveness. Here's a quote from another paper written by Jack Dongarra and others in 1993. He said that the implementations of numerical algorithms should resemble the mathematical algorithms on which they're based. This is in contrast to Fortran 77, which can require complicated subroutine calls, often with parameter lists that stretch over several lines. In Crystal, your code can be as expressive as your theories. I should know, this was my talk at the previous Crystal conference. The theoretical physics I was doing during my PhD was done with just pencil and paper, no arithmetic, because it was abstract. So I was determined to write a library that could do the same task without losing that abstract beauty. So this is a diagram that shows the relationship between two of the libraries I made. The first provides base classes that anyone can use to do their own research in symmetry, hence the name SymBase. And the second inherits from those into a little bit narrower subtopic of the 32 point groups, hence Sim32. It turned out that using these libraries, I was able to do my same pencil and paper research without having to translate it over to computer code version and thus reduce it to just number crunching. The dream of expressive code is a reality with Crystal, I can say. I think our second selling point is organization. Every scientist knows the value of clear ideas and organization of thought, like the picture on the left. And yet we researchers too often find ourselves writing a pile of sprawling, unfocused functions, more like the picture on the right. They're difficult to understand and they're difficult to use because sometimes you just can't find that one tool you need. I'm not saying it's impossible to write messy Crystal code, but as you saw in the CSV example, the standard library is very clean and organized. This is a convention that I learned in Ruby, and it changed the way I saw programming. Small, focused classes, modules, functions, everything. The language supports this pattern of abstraction, and the pattern supports the language. What's more is that Crystal goes a step further than dynamic languages like JavaScript or Python by making the expectations explicit. So here's a code example. This is pretty typical scientific research code. Unfortunately, code like this is often written once and then thrown away. And that's because there's this very tight binding in between the code I wrote and the problem I was solving that day. So I had some data and I wanted to process it. So I wrote a function called process data. You can imagine it's 100 lines long. And right off the bat, we can already see that I'm kind of reaching into data and making assumptions about its shape and its type. And this just isn't possible in Crystal. The compiler is going to complain about this, but it's going to complain in a very helpful way because my experience has been that as soon as the compiler stops me from writing this kind of stuff, then I have to think just one level of abstraction higher because it can't quite infer the type in cases like this. I get two benefits from this. The first one is just clarity of thought. So if I was writing this in Crystal, then the first thing I would do is create a namespace for my study. Let's call it study A. So module study A. Then the next thing I would do is use a struct. I can use the record keyword to make a struct. I'm calling it patient data and make it really explicit what exactly the shape was of that data that I expected to be coming in. That's only a little bit more code, but the result is a function which is almost identical to the first, except now I'm just explicit about that expectation. I'm explicit about that type binding. I just had to that light bulb needed to come on that I was doing that in the first place, which often will lead me to rewrite it and say, hey, I don't want that to be so tightly coupled, but not always. Sometimes it's the right thing to do. But I get that clarity of thought. And what's more is I get reusability. So let's say that a few months down the road, I'm coming on study B now. I've published the old paper, I'm on to a new one, and I've got something similar going on in my data, and I really want to reuse that code that I wrote 4 months ago, but I can't because the new data is a slightly different shape. Well, this is pretty easy now in Crystal. The compiler, wherever I handed it the wrong shape of data, right at compile time will stop me and say, hey, you've got a few functions that are expecting this shape here. You got to do something about that. And there are a lot of approaches how to solve that. One of them, perhaps the most brute force, would be just to overload process data and say, If I hand you study B's patient data, then do this, make this slight variation. Our third selling point for scientists is that compiler that I've been talking about. It's a very friendly compiler. As a scientist, whenever I used to think of a compiled language, then I would remember a wall of dense warnings and errors that were difficult to decipher as a non-expert in the field. Let's have a look at what the Crystal compiler produces with code like this, which is usually, A is normally an integer, but in some cases, pretend that this has many files and many hundreds of lines. There's some way for it to become a string. Now that might be difficult to spot, and you would have a runtime error in a dynamic language. But of course, with a statically typed language, the compiler will catch this, and it'll give a very friendly message. There's a nice little green arrow that points directly at that addition operator and says, no overload matches string plus with type int32. So it's saying, hey, you tried to call the plus method of the string class, and I don't know how to handle that. You never told me how to handle int32. I know how to handle another string, and how to handle a char. So how do you want to solve this problem here? Did you do something wrong over here? Do you want to create an overload? The options are open, but the message I got back from the compiler is very friendly and very helpful. Crystal is like other modern languages in that the core language maintainers are providing documentation generation, a test suite API, a runner for it, a code formatter, and these are all really great things. But in Crystal, we actually go a step further by including these tools directly in the same command line tool as the compiler. That means if you have the compiler, you have all you need to follow best practices like these. That might seem like a small perk to a professional developer, but consider this from a scientist perspective. Many of us have never heard of documentation generation. We've never heard of unit testing. We've never heard of code style or code formatting. And the extra friction that we see in other languages like Rust and Go of having to install and learn to use any extra packages just kind of gives the impression that these things are optional or maybe too much trouble. The choice to put these things directly in the compiler binary is, in my view, a stroke of genius. It gives scientists a leg up in the developer world that they so sorely need. And speaking of which, the compiler also has built in this playground server. So lots of languages host something like this online, but with Crystal, it's included in the same compiler executable. So I can actually directly from my command line type in Crystal play, and then on my local host, I'll have this playground spun up where I can type up my code on the left and see the runtime values of the code on the right, which is great for debugging. But what's more is that whatever directory that I spun that up in is the place that I will be able to require other code from. So I can pull in massive libraries, which means that the complexity of this can actually be pretty high. And I'm not sending my code off to some server out in the cloud. I'm keeping it right here local. So there's privacy, there's greater complexity. And again, it's right there with the compiler. So no extra steps included. It's an awesome tool. Our fourth point that I like to highlight is the flexibility. So as I mentioned before, Crystal is flexible enough to work at all levels of this tool hierarchy. So as a scientist, I might need to customize something really at any level of that stack. It could be the math library down there at level 0, it could be the package I'm working with. And Crystal actually makes it possible to customize really nicely. I listed just a few options here. One of them is that the library you need to customize may have just provided a nice type or an interface for me to implement. They might have provided some base classes that I can inherit from, like I did with my symmetry work. They might provide a module with a bunch of methods they can mix in and take on the strength of whatever that was. And then, of course, like Ruby, Crystal has open classes and modules. So maybe as a last case scenario, I can always just reopen the old definition and customize it to my needs without having to actually change anything about that source code. Really handy. So after all this, we can still ask, why? And yes, an important answer to that question is that I want to see the Crystal language live a long and healthy life. But I don't just want to talk about the longevity of Crystal. I believe in the humanity of technical pursuits, the technical arts, if you will. And it's these technical arts which are in danger of suffering a premature death in the digital world. To me, this is not just mere hyperbole. Have you ever learned a principle of mathematics that felt like it belonged to the humanities? I have. I remember learning about partial differential equations many years ago in college. It is not an exaggeration to say that my fellow students and I were overpowered. We said, wow, this idea is so beautiful. It describes so much with such clarity and such flexibility. This is the kind of experience that belongs to the technical humanities. To help you get a feeling for what I'm talking about, I hope you can forgive me for quoting extensively from a source which perfectly sums up my feelings about programming. In this quote, every time the author talks about math or mathematics, I want you to hear in your mind code or programming. This is from A Mathematician's Lament by Paul Lockhart. He said, "It would be bad enough if the culture were merely ignorant of mathematics. But what is far worse is that people actually think they do know what math is about and are apparently under the gross misconception that mathematics is somehow useful to society. This is already a huge difference between mathematics and the other arts. Mathematics is viewed by the culture as some sort of tool for science and technology. Everyone knows that poetry and music are for pure enjoyment and for uplifting and ennobling the human spirit, hence their virtual elimination from the public school curriculum. But no, math is important." The author then asks himself, are you really trying to claim that mathematics offers no useful or practical applications to society? And then he answers, of course not. I'm merely suggesting that just because something happens to have practical consequences doesn't mean that's what it is about. Music can lead armies into battle, but that's not why people write symphonies. Michelangelo decorated a ceiling, but I'm sure he had loftier things on his mind. The same is true of code. Scientific code can and should be beautiful. I see it in math and in the sciences, and I see it in code. It's sad to me to find so many beloved theorems and proofs in pure math reduced to loveless number crunching on a computer. I feel in my heart that it could and should be beautiful too. I strongly believe that scientific code should elicit the same rhapsodies of the heart that the theories themselves elicit, if not more, and certainly not less. So I say, if you want to write beautiful code, write it in Crystal. If you still want to be writing Crystal in 40 years, then express the beauties of science and math in Crystal. It's your code that could be studied and talked about 40 years from now. Let's go make that happen. Thank you.
Thank you, Casey. Great talk. Feel like I've been to church. I can see a question from Beta. Great talk. What are the rough edges you find in the language from a scientific perspective? So let's take this one and then go to the chat.
Cool. Yeah, the rough edges, I mean, I think I've heard it a couple other times at the conference here today as well, that sometimes you do have to kind of deal with the type system. Sometimes you find yourself being like, okay, what does it expect? And you have less of that like kind of fun experience of dynamic languages bring. But I would say I was surprised to find how rarely that happened for fairly large and complex projects when I was working in science. And many times I started off annoyed and then became like pleased that the compiler was able to like coach me through that. You know, that was an experience that happened multiple times. One of the reasons that I kind of wanted to give this. But yeah, that'd be one rough edge still.
Thank you, Casey.